Hello, it's Stat 134, Lecture 23. On Wednesday, there's a special lecture on the moment generating function. This is not covered in the book, but will be quite important for this course. Last time, we started the gamma distribution, section 4.2. So remember T, the exponential distribution, has the density lambda e to the minus lambda t. Here e to the minus lambda t is the variable part, and tr gamma r lambda, where r and lambda are both real numbers greater than 0, has density involving the gamma function lambda to the r, t to the r minus 1, e to the minus lambda t for t positive. So gamma of r is r minus 1 factorial when r is a positive integer, and when r is a positive integer, interpretation of the gamma is that it's the time to the rth arrival of a Poisson lambda process. So the main trick in calculating gamma is the probability that tr is greater than t is equal to the probability that that n sub t is less than r. In other words, the probability that the rth arrival takes longer than time t is equal to the probability that less than r arrivals occur in time t. So today we're going to start section 4.4. We're skipping 4.3. The change of variable formula for density will be the main focus. We'll also talk about recognizing a distribution from the variable part of its density. So here's the change of variable formula for densities. Let's consider x standard uniform. Here the density is just an indicator, which is 1 when x is between 0 and 1 and 0 otherwise. So what's the density of 2x? Well, clearly 0, 1 gets stretched out to 0, 2, and since all the probabilities between 0, 1 for x, all the probabilities between 0, 2 for y. So the height then would be 1/2. So the density is 1/2 times the indicator that y is in 0, 2. Now here our transformation of x is linear. In other words, it's just g of x is 2x. And you can see that y is in dy if and only if x is in dx. What if our transformation isn't linear? So here's an example where our transformation, let's say, is many to one function, g of x, 3 to 1 function in particular. So here the preimage of y as shown is x1, x2, and x3, and y is in dy if and only if x is in dx1 or x is in dx2 or x is in dx3, and those are mutually exclusive events. So then by the addition rule, the probability that y is in dy is the sum of probability that x is in dx1 plus probability x is in dx2 plus probability that x is in dx3. And we can approximate these probabilities with our density. So we get fy of y dy is the sum of these f x I dxi's, and dividing by dy gives us this formula where now we have dxi over dy, which we can write as 1 over the derivative of g. So we get the sum of fx xi over the derivative of g evaluated at xi. And so notice here, I forgot to mention that we write the density of y as f sub y of y, and the density of x as f sub x of x. So we'll be writing the letter of the random variable under the f to denote which density it's corresponding to. So this essentially is the change of variable theorem. The only thing that's missing here is that we would, since fy of y is a function of y, we would want to write xi as a function of y. And so let's just take a look at the theorem here. X is a continuous random variable with density fx of x. Let y be g of x. Have a derivative that's 0 at only finitely many points. Then we have this finite sum over all x such that g of x is y, fx of x over the absolute value of g prime of x. Oh, I forgot to also mention that we take we divide by the absolute value because each of these terms is a probability, so it needs to be positive. And for example, in this case, the derivative at x2 is negative, so we need its absolute value. And finally, we need to evaluate at x the pre-image of y. So let's just see an example. If x is standard normal with the given density here, we want to find the density of this linear transformation and where sigma is greater than 0. So the g inverse of y, in other words x, is y minus mu over sigma. So when we apply the change of variable rule, of course we only have one term because this is a linear function. We get fx of x over sigma, because sigma is the derivative of g of x. But then we need to evaluate it at x equals y minus mu over sigma, and there you go. So that is the change of variable theorem, and here x runs from minus infinity to infinity, and so since sigma is positive, y also runs from minus infinity to infinity. And I should also mention that the expectation invariants are mu and sigma squared respectively, and it's not clear yet that y should be normal in this case, but it turns out that 2 times a normal is normal, so y belongs to normal mu sigma squared, but we'll see that later on. So here's the change of variable formula for a more complicated example. So x is uniform minus 2, 2, which has density 1/4 times the indicator that x is in minus 2 to 2. And we want to find the density of x squared. So, now I've written a picture of the density of x, and so obviously y will run from 0 to 4, which is important to note, and x is plus or minus the square root of y. So if I apply my change of variable rule, I'll have 2 terms because this is a 2-to-1 function. I get a quarter, so I get the density of x divided by 2x, because 2x is the derivative of g, and then I plug in square root of y, and then plus the same thing, but now I plug in minus the square root of y, and I need an absolute value where I have the 2x because I need a positive probability there. So when you do this, you get 1/4 times the indicator that y is in 0, 4, square root of y. And so I've made a graph of this here. So then I had you guys work on this problem. Suppose the random variable x, measuring the magnitude of an earthquake, follows exponential. We want to study the distribution of the total energy of earthquakes. Find the distribution of y is e to the x. And I've given you the change of variable formula here. So we have x exponential, I know that density. G of x is e to the x, that's 1 to 1, so I'm only going to have one term in my sum. And x is log y. So the rule gives me f of x over the derivative of g, and then I plug in x is log y, and then just applying some algebra, I have the density of y. So next, we're going to recognize a distribution from the variable part of its density. This can be a very useful trick. So a density can always be written as a constant times the variable part. And the important thing to understand is that when you integrate a density, you get 1, and you can pull the constant out of the integral. And so the constant's actually determined uniquely from the variable part. So if you know the variable part, the density is pinned down. And it's often advantageous to ignore the constant part because you can always derive it. And if you can recognize what density the variable part belongs to, then you know what the constant is. So let's see some examples of this. So I've written down 3 distributions here and their densities, and I asked you to circle the variable part. So the variable part, for example, of gamma is t to the r minus 1, e to the minus lambda t. And so if I recognized this, if I recognized that the variable part of a distribution was this, then I would know that the constant part has to be 1 over gamma r lambda to the r, because that's the density of a gamma r lambda. So recognizing the density part, recognizing the variable part tells you what the constant part is, and can save you a lot of work in calculations. So I ask you here to recognize the distribution that these are the variable parts of. And so, for example, the first one, if you see t cubed e to the minus 1/2 to the t, you recognize t is t to the r minus 1, so r is to the 4, and it's e to the minus lambda t, so lambda is a half. You can tell the difference between, for example, b and c, because a normal is always t squared. We finished with a concept test here. V is a standard normal random variable. The distribution of x equals v squared is. So v is standard normal. I know its density. I have 2 terms in my sum of the change variable rule. I plug in v as plus or minus square root of x. And now I'm going to ignore the constant part. So this is proportional to e to the minus x over 2 over square root of x, which is x to the minus 1/2 e to the minus 1/2 x. So right away I see that the variable part is, I see from the variable part that it's a gamma with r is 1/2, lambda is minus 1/2. And so that tells me what the density is, and so then I know that the constant part is what's in green here. Okay, so I will see you next time. Have a great day.